As part of the Bargain Colloquium, we don't have any lectures this year because of everything that's going on, but Professor Suarez agreed to come and give the talk as part of the colloquium, so we're very grateful. Mauricio Suarez held positions at Oxford, Andrews, Northwestern, and Bristol universities, and at present he's a full professor in logic and philosophy of science at Complutense, I hope I pronounced it correctly, University of Madrid. I know Professor Suarez's work, very influential work in representations and modeling in philosophy of science. And recently he has a new book that came out called Inference and Representation, a study in modeling science. And I think he's, I don't know if single-handedly, but very importantly started a tradition in philosophy of modeling, which is neither just similarity relations between models and target systems, and neither isomorphism, which is the other tradition. But he started really an independent way of thinking about modeling. So very exciting to see this book come out, which spells out the position in much detail. Recently, his work has turned more historical, he tells me. And the talk that we're going to hear today is about propensities in philosophy of probability. So the title of the talk is The Possibilities in Propensities, which I think represents a different chapter, maybe perhaps, than what we know Professor Suarez's work primarily. So, thank you.
Great. Well, thank you. Do I need to speak to the microphone? Is that right? I need to hold the microphone, correct? And speak to the microphone?
I think we hear it.
But for the people on Zoom?
They hear it.
They hear it.
Microphone or not? Yes.
Microphone, yes. I need a microphone. There's a preference for microphone.
In the back there.
Yes, good. Well, thanks very much for the invitation. Thanks very much for the introduction. I was at Hebrew University yesterday as part of the Bar Hillel colloquium, and I talked about that book. Today, I'm not planning to talk about that book, so those of you who came for that, I fear maybe a little disappointed. But you can ask your colleagues over at Hebrew University about what I said yesterday, and they tell you about that. So what I wanted to do today is to talk about my other project. And for some time now, I've been having these two concurrent projects ongoing. One of them is the historical project and philosophical project on representation, which culminates in that book. And the other project that I've been doing for a very long time now is a project on the philosophy of probability, trying to understand what is it that we need to do as philosophers to understand scientific practice in statistical modeling practice, in particular in the range of different sciences. And this, again, is culminating also in a series of papers and a slim book that came out with Cambridge University Press, one of these Cambridge elements, a couple of years ago. And what I'd like to do today is to give you my latest thoughts on this project. So I'm afraid not a lot of history, except that I'm going to talk a little bit about the history of my interest and involvement in the philosophy of probability and the people that were influential to me while I was developing this work. But other than that, this is pretty much a philosophical talk that concerns the interpretation, the philosophical interpretation of probability. So I want to start by doing a little bit of personal history. And that's to say that a lot of the work that I have done in this field is very much indebted to Paul Humphreys. He was, or should I stand? Maybe I should stand here so that you can actually see the screen, right? So Paul Humphreys, British a philosopher who developed all his professional career in the US. Was an interlocutor of mine on these topics for a very long time. And a number of things that I'm going to be talking about today are, I'd say, influenced, if not heavily indebted, by his views and his ideas over the years. He died unexpectedly a couple of years ago, very sudden, quick illness. And I miss him. Actually, I find that I used to always send him an email with my latest paper, and he would reply, and we'd have a little exchange and so on. And now I'm producing these papers, and I don't know who to send them to. I'll look at that picture and think, oh gosh, well. So the paper that this talk is based on is dedicated to Paul, and the talk is also in a way dedicated to him, and you will see that his ideas do make an appearance at different points during the talk. And so this tells you a little bit of my history, the history of my involvement with probability ideas. It comes, a lot of the ideas that I'm going to discuss here originate in this Springer book that I put together on probabilities, courses, and propensities in physics, with a bunch of different contributions from different people, philosophers and scientists who were thinking about the concept of probability then. And it had this unusual angle in that we're discussing causation and propensities, which are essentially dispositional probabilities or probabilistic dispositions in the context of the philosophical interpretation of probability. That was pretty unusual at the time. Most philosophers of science were then still taken by the frequency interpretation of probability, which makes no use of these notions. So this was sort of something that was in some ways new. And then I followed that up with a couple of more papers. That paper called The Chances of Propensities came out in BJPS, and is the outcome of 2 years of work while I was at London's Institute of Advanced Study, working on a Marie Curie project on probability. And the Cambridge Element book is the latest thing that I published, which is a kind of compendium of basically all my main ideas about probability in general. And this, I guess you have to add up the fact that this paper just came out, and this is a paper that is heavily indebted to Paul, dedicated to him. And here I put forward a particular angle on the notion of propensity, which in previous work was left unanalyzed, but here I sort of give an account of what propensities may be. And this is what I mainly want to talk about today, the contents of this paper. I have to tell you a little bit about how this project has developed over the years and how it eventually ends up in this final paper and the views that are defended in this paper. So this is the plan for the talk today. I'm told that I have 50 minutes, so I think I can make it, just about. I want to first of all tell you a little bit about my historical project, starting off in 2011, and that's a defense of pluralism about objective probability or chance. I want to put that in the framework of other defenses of pluralism that have been made throughout the years and connected to some other kinds of pluralisms about probability that you may be more familiar with. Then I want to talk about propensities in the way that they are presented in the previous work that I discussed as what I call index function representations of chances. And then I want to focus on a little bit of practice of statistical modeling, and I'm going to use a very simple example, which is the coin toss. So although this is intended to apply to all kinds of areas of science where statistical modeling is prominent, including quantum mechanics, statistical physics, quantum chemistry, many other areas, evolutionary biology, many other areas in science where statistical modeling is prominent. I'm not actually going to discuss any science other than the coin toss, which you may think is a very simplistic system, but maybe not so simplistic. Just wait until we get there. And then I want to put forward my view on probability, which is this so-called tripartite conception of objective probability, linking it up to notions of possibility, and finally just end with a few examples of how to put this machinery to work in the elucidation of some more complicated cases and real scientific cases of statistical modeling, both in quantum physics and evolutionary biology, but that will be very quick, and I won't get into many of the details. You can ask me more in the question time if you have questions about the details. So I want to start with discussing other forms of pluralism about probability that you may be more familiar with, because this is not the first time that the pluralism about probability has been defended. You find pluralist views about probability in the works of Frank Ramsey, Ian Hacking, and Rudolf Carnap. Different kinds of pluralisms in each case, arguably, but in all cases, a sort of pluralism that divides probability into cleanly two different notions, or two different sites, or two different kinds of phenomena. One is probability understood as subjective or epistemic notion, that is probability as a measure of our ignorance regarding a particular phenomenon or outcome of some given phenomenon. And the other one, probability as an objective phenomenon, something that actually occurs in nature. So the first kind of probability is supposed to measure something about our state of knowledge or ignorance. It's supposed to tell you something about the contents of our cognition, and in particular about the lack of complete or full information that we may have about a given subject. So when we don't have full information about a given domain, we have to employ probabilities, and those probabilities essentially are measuring our ignorance about the full detailed story underlying the phenomenon. That's one way in which we use probability as a measure of subjective states, cognitive states, as a measure of lack of information, as some sort of epistemic notion that measures our state of knowledge. But the other way in which we use probability is that we consider phenomena that take place in nature, and we ascribe objective chances to that phenomena independently of our state of knowledge. So there are some phenomena that we consider to be inherently chancy, and the inherent chanciness of the phenomena, of those phenomena, is not in any way reliant or dependent on our state of knowledge. Even if we knew everything that there is to know about those phenomena, they would still appear probabilistic or indeterministic because they are inherently chancy. Quantum mechanics is perhaps the paradigm example of this, but there are other areas in science when we have to confront phenomena that appear inherently chancy. So you already see in Ramsey, and in particular in Hacking, in the Emergence of Probability, the study of how probability emerges from the 17th century as an essentially dual notion. It both measures lack of information, it's an epistemic notion, and it also measures something objective that happens in nature that produces certain results with a certain objective inherent probability, and therefore it's ontological. So probability from its very inception is both epistemic and ontological. It has this kind of dual aspect. And people who take this to heart and distinguish, therefore, two different concepts, probability sub 1 or probability sub 2, are the concepts introduced by Carnap. Carnap was very given to naming concepts by just indexing them with numbers. So probability sub 1 was the sort of subjective or epistemic probability that I was talking about. Probability sub 2 for Carnap is the sort of ontological objective probability. So this is widely accepted. I think everybody who works in the philosophy of probability accepts, well, not everybody, but almost everybody, except for a set of measure 0 of people, accept that there are essentially two sides to probability, or two distinguishable concepts here that you have to deal with differently. It's sort of subjective epistemic probability we call credence, the objective or ontological probability we call chance. So actually everyone working in the philosophy of probability is already a pluralist. Okay, so I'm not committing any kind of heretical act that is completely unforgiving by introducing more pluralism into the picture. We're already all pluralists when it comes to probability. But I do want to go farther than these authors, and I want to claim that even when you look at just objective probability or chance, you also need pluralism there. You need to divide objective chance and to distinguish different notions in our analysis of objective chance. This is even disregarding everything that we may be able to say about credences. And you have to distinguish these three different notions. You have to distinguish what I call theoretical propensities, or in the literature, they're well known to be propensities or probabilistic dispositions, from what I call single case probabilities, which are formal features that appear in our models, from frequency statistics. And you may ask, well, yes, of course, you have to make these distinctions. Isn't this trivial too? Isn't this kind of pluralism trivial? Just as the previous kind of pluralism seemed trivial, this seems trivial too. Well, this one isn't so trivial, and you'd be surprised how many philosophers are prepared to deny this tripartite distinction of objective chance into three different conceptual notions. In fact, the whole of the philosophy of probability throughout the 20th century could be summarized as a series of attempts to do away with those three notions and reduce them all to one. So the propensity interpretation of probability, made famous by Karl Popper, of whom I'm sure you know here, the propensity interpretation of probability is an attempt to do away with probabilities and frequencies, reducing them all to propensities. The so-called frequency interpretation of probability, which originates with the logical empiricists von Mises and Reichenbach famously defended it still has some champions, still decreasing number of defenders, but it still has some champions. It's an attempt to do away with propensities and probabilities and reduce them to frequencies, and claim there are only frequencies in the world, and everything that seems mysterious about the concept of objective chance is reducible or can be understood in terms of frequencies and frequency statistics. So there have been lots of philosophers who have denied pluralism about objective chance implicitly. And so what I'm doing here is a kind of part of a larger pluralist project, but at the same time, it goes against a lot of the philosophy of probability tradition of the 20th century. But I'm happy to report that we're an increasing number of pluralists, and maybe not everybody would divide objective chance in the way that I do, but many people nowadays claim that you need more than just one notion to make sense of what is a very complex phenomenon, objective chance. So I'm going to basically argue for this tripartite conception of objective chance here, and I'm going to be providing some arguments for why we should accept this tripartite conception. But the most formidable argument for pluralism about objective chance and the tripartite conception is really the failures of all the different attempts to reduce probability to either propensity or frequency. And I'm not really going to talk about that, but you find that in my previous writings and in the writings of many others who have written extensively about this, criticizing and providing very convincing arguments, I think, for why you cannot reduce objective chance to either propensity or frequency. And you really need to have the three notions somewhere in your picture when you're analyzing this complex phenomenon. If you want to know more about this, and if you want, I mean, I could talk about this all day, but if you want to talk about this in the questions and answers periods, we can do that.
Hello?
Later. All right. You have the privilege of the first question. Gain that. So anyway, here's the paradigmatic example of this sort of pluralism that I defend. The coin toss, famous example, and you may think this is very simplistic example. I argue it's not so simplistic, and it's in many ways a very good paradigmatic example. When you toss a coin, you can talk about the propensities of the coin to land heads or tails. And that's supposed to appeal to some features or properties of the coin in itself. The landing of heads or tails with a certain probability appeals to a certain property of the event of landing heads or tails, which is not exactly the same thing as the coin in itself. So the probability is a property or feature of the landing heads or landing tails event, which in my account is a manifestation of the underlying propensity. And this again is tested by running experiments on coins and tossing them many times and collecting frequency statistics for the coin. And then you can test your ascription of propensities and probabilities in accordance with this frequency statistics. If the coin is fair, you're going to expect roughly a 50-50 distribution between landing heads and landing tails in the frequency statistics. But if the coin is not fair and is loaded, then the expectation would be different for the frequency statistics. But you can see how implicitly the three notions are already playing a role in this very simple example. There's something about the coin in itself, that's the propensities in the coin. There's something about the event of tossing the coin. I mean, there's lots of things you can do with the coin, but if you toss it to see if it lands heads or tails, then you're going to be testing for the probabilities of certain events happening. And then finally, you can collect the statistics and get a laboratory technician, because it's really boring to do it yourself. So you get some young PhD student to do it, so throw the coin many times in the air and check what the statistics are that come out of that. And that's a different notion. That's the frequency statistics that come out of the running of the experiment. So I want to argue this, which seems trivial in the case of the coin toss, is universal. And every chance phenomena has this feature that you can distinguish these three different concepts. And it's important to be able to distinguish them.
Can I ask a clarificatory question?
I don't know if I can let you do that. But you're the chair,
Yeah,
so I guess.
But it's the same probability, right? For the coin toss. For the coin toss, the same number.
What do you put the same number as what?
It's either one, if it's one half.
If the coin is fair.
If let's say the coin is fair, so
then it's 50.
These are different notions of probability relating to the same number that I'm thinking about.
They're not different conceptions of probability. They're different notions, concepts. They're different, appealing to different properties of different entities, and they all play a role in our description of this chancy phenomenon. So I'm going to be arguing even tossing a coin is a complex phenomenon. It's not as simple as we think. And the ascription of probabilities to that phenomenon requires you to distinguish these three different levels of properties. Properties of the coin, which are dispositional, properties of the events, which are probabilistic, and properties of the experimental run, which are frequentist or frequencies. And they're all involved in our understanding of what it means to toss a coin and get an outcome that's chancy. And so my picture, every chancy phenomenon is complex in this way, even tossing a coin, which is the simplest that you can think of. It's complex in this way. So anyway, I think, yeah, I'll answer all your questions at the end. Probably it'd be easier once I tell you the full story and you see how the pieces fit together. So why is this important? This tripartite distinction is important because there's something in the literature called Humphreys paradox, which is something that we owe to Paul Humphreys, which shows that you cannot identify propensities and probabilities. Humphreys was one of his main contributions was an argument, very influential argument, which some of us think is one of those wonderful philosophical arguments that change a field. Which shows, some of us believe very conclusively, that you cannot identify probabilities and propensities. They're not the same thing. And he has, I can't run through the whole experiment. Maybe I can explain it in the question and answer period. It's all over my writings in the past. It is basically a thought experiment in which he shows you that if you identify probabilities and propensities, you run into all kinds of contradictions. And the only way out of the contradictions is to distinguish propensities and probabilities. So in response to this challenge, the Humphreys paradox, what I've done in my work, and this has been a constant of my work ever since I started working on this topic, is to distinguish the propensities or probabilistic dispositions, and to claim that these probabilistic dispositions are merely displayed in probabilities of events. And unlike deterministic or surefire dispositions, these probabilistic dispositions are manifested only with a certain probability. So those of you who know the notion of disposition, the paradigmatic case is the fragility of a glass. A glass is fragile not because it's broken, but because it can be broken if you hit it sufficiently hard. It has this disposition to break when you hit it with a hammer. That's what makes it fragile. But that's a surefire disposition. If you hit it sufficiently hard with a hammer, it will surely break. Propensities or probabilistic dispositions manifest their effects only with a certain probability. That's the difference between a surefire or deterministic disposition and an indeterministic or probabilistic disposition, also known as a propensity. Okay, so what I've been arguing in all these years, in all these works of mine, is that the propensities should be used not to interpret the probabilities, as Popper wanted to do and failed miserably to do, but propensities serve to generate and therefore can explain the probability functions that display them. And I'm going to show you how this works in the case of a coin toss in a minute. What happens there is that the coin has certain probabilistic dispositions, which are inherent to the system, to the coin as a system that we want to study. And those probabilistic dispositions are, under certain circumstances, displayed as probabilities. If the coin is fair, those probabilities will be 50-50 for heads and tails. And those probabilities are defined over what we call the outcome space or the sample space of the probability function. And how to select what goes into the outcome space is really critical when you're doing statistical modeling in any science. And I claim that's very intimately related to your ascription of propensities to the system in the first place. This is important. Why? Because if propensities are not identifiable with probabilities, then you cannot claim that the propensities inhabit the outcome or sample spaces that the probabilities are defined over. Technical notion, I know, but it's important to know this because once you know this, you can get around Humphreys paradox. This is the way to resolve Humphreys paradox and not to fall into the contradictions that that Paul studied and showed us that you get into when you identify probabilities and propensities. So what's wrong with Popper's propensity interpretation of probability, infamous propensity interpretation of probability, is that Popper identified the probabilities with the propensities, what we nowadays call the propensity identity, and that led to all kinds of problems and contradictions. It's the same problem that Paul Humphreys discussed and led him to the contradictions. The way to get around all these problems is to keep the two concepts distinct and to claim that the propensities merely generate the probabilities and explain them, but cannot interpret them. They're not identifiable with them. They're two different things. You have to keep them separate. Propensities generate probabilities, but they're not identifiable with those probabilities. If you do this, I promise, trust me, you get around all the problems. None of the problems in the philosophy of probability have given people so many headaches are problems for you if you distinguish propensities and probabilities in this way. I may have other problems, but I don't have the old problems. One interesting thing about this, you may think, well, he's distinguishing propensities from probabilities, so he's saying that there's a fundamental basic level of propensities. No, I'm not saying that. You can have nested propensities all the way, and you can have propensities to manifest themselves, and propensities to manifest themselves, all the way down, as Alexander Bird and Hugh Miller used to say, it may be dispositions all the way down. So you get all the way down to the reductive base in quantum mechanics, and you still find that you have propensities there. That can happen. Nothing in my account militates against that. So if you think this is an objection, if you think, oh, he's just basically postulating that there's a basic ground level of dispositional facts that you cannot get beyond. No, I'm not saying that. It's just a matter of how you describe the relationship between propensities and probabilities, but I make no further assumptions about what kind of propensities or probabilities there are in the world. So in the case of the coin toss, that I said before, what does this all mean? What this means is that you have to think of the coin as having the probabilistic dispositions in and by itself before you even toss it. The coin is a system that has certain given properties, physical properties, and part of those physical properties determine already some propensities. Then once you put the coin in motion and you toss it in an experimental setup where you're just going to throw the coin in the air and see how it falls down on a hard surface. For this, you need an experimental setup. Then that will generate a sample space of events, of outcome events, landing heads, landing tails on the table, over which the probabilities will determine certain probabilities or single case chances. Even in the case of a single toss of the coin, you're going to have a certain probability for it landing heads, landing tails, determined by in part by the makeup of the coin in itself and its propensities. And then you can just run an experiment on this when you repeat the tossing of the coin many times and collect frequency statistics, and that will help you to test the ascription of both probabilities to the tossing event and the propensities to the coin as an individual or independent system. So this is what you need to do in order to distinguish these three notions carefully and to make sense of the example of throwing or tossing a coin. And this is kind of incredibly, to my mind, when I first started thinking about it, this is incredibly fresh and new for philosophers who haven't really thought very hard about coin toss as a dynamical system and have just assumed from the beginning that a coin toss is a simple phenomenon where you ascribe, by means of some principle of indifference, a certain probability to the falling heads and the falling tails of the coin. So you inspect the coin, you see that it's perfectly symmetrical. You have no reason to privilege one of the sides over the other, and you just give probability 1/2 to the falling of the coin on heads or tails, just out of this consideration of indifference. And people just discuss the coin toss as if it was this simple example where it was trivial. That if the coin is fair, then of course it has the same probability of falling heads and tails. What else could it be? But if you do this, you're not really looking into the coin toss as a dynamical phenomenon at all. And you're not thinking about the coin's properties as part of this complex dynamical system, which you have to do because it is a more complex phenomenon than you think, tossing a coin dynamically. In actual practice, what we do is we construct a model for the coin toss by using Newtonian classical mechanics and filling in a full picture of the coin toss as a dynamical mechanical Newtonian system. You have to make lots of assumptions in order to get this model off the ground. And these models have actually been produced. Mathematicians have produced these detailed models of the coin toss, but only relatively recently, in the last 25 or 30 years. Nobody cared to model the coin toss before that because everybody assumed it was trivial. But it's physically a very interesting system, in fact. And you have to make a bunch of long bunch of assumptions in order to get this model off the ground. Every model is predicated on a bunch of idealizing assumptions, and this is the case too for the coin toss. You have to assume, Keller did this for the first time that anybody did. Dynamical model of the coin toss was Joseph Keller in 1986. You have to assume the coin's radius is a certain number, which stays constant through the tossing of the coin. Well, that's already an assumption. That the coin's thickness is negligible in the dynamical motion of the coin. That the coin's center of gravity is its geometrical center and is found at some height to begin with when you first toss it. Not a trivial assumption, because if you bend the coin, then the geometrical center and the center of gravity or mass will not coincide. So this is already a big idealizing assumption about the coin. That the coin's initially at a certain height from the surface, that the coin does not rebound, that it falls flat on the surface, because otherwise you have a more complex dynamical system that you have to model as well if it rebounds and keeps bouncing. That the coin's angular velocity remains constant throughout. if you don't make this assumption, you cannot model this system as a dynamical system because we don't have the mathematical tools to do that. So you assume that the angular velocity is constant throughout the motion.
It's not the same A, right?
Mm.
No, it should not.
No, it's not the same A. Well, actually, you can make it the same A. There's no reason why it shouldn't be the same A, but it doesn't have to be the same A. No. So that's basically the idea that you have a coin, this negligible thickness, a certain distance, a certain radius, and you toss it with a certain upwards velocity and a constant angular velocity. An upwards velocity of a certain value and a constant velocity of a certain value. And when you do that, the only three parameters in this model are then those two initial features of the coin, the angular velocity and the upward velocity. Everything else, it becomes just a fixed parameter, not a free parameter in the model. And then what Keller did is that it's possible to show that the Newtonian mechanics of the coin's motion determines certain pre-image areas in the phase space of these initial conditions, the angular velocity and the upwards velocity, corresponding to the outcomes at landing. So that means for every combination of angular velocity and constant velocity, it will either land heads or tails. And you can describe that phase space, initial phase space of those two initial three parameters. And then what you find out when you do that, this is well known to people who know something about the method of arbitrary functions, inaugurated by Poincaré and others, is that a sufficiently smooth distribution of those initial values of those two parameters is going to give you a perfectly regular distribution of heads and tails in the final outcome space. So you're going to have exactly 50-50 chance for heads and tails when you consider that a smooth distribution over the initial parameter space. So the probability of the coin landing heads or tails becomes independent of the symmetry of the coin, of the random distribution over its initial position. You just need to have a sufficiently smooth distribution of initial values of those two initial parameters to get the derivation of the 50-50 probability out of the dynamical model. And this is all in spite of the underlying determinism of the dynamics. I mean, we know this is a Newtonian mechanical system, so it is a deterministic system, but the smooth distribution over the initial values of the parameter space guarantees that you get the 50-50 probabilities out at the end of the outcome. What do you call it? And not
Ignorance.
Ignorance.
Yeah, not a measure of our.
Well, you could call it that. If we could be very precise in the initial values of position and momentum, then we could determine exactly whether the coin would fall heads and tails. But since we cannot be perfectly precise, and there is a debate about what this smooth distribution is, whether it's epistemic or objective in this literature. Since we cannot determine that, you can only give the probabilities at the end. Is this a result of our initial ignorance? Is this a result of the fact that we cannot very precisely toss a coin with a given initial angular momentum and upwards velocity? That's debated. But what's not debated is that you get these probabilities at the end. So we call them chance because of probabilities in this phenomenon. But whether they have some kind of epistemic origin or not, it's debatable. That's debatable. What's not debatable is the theorem that shows this out of this dynamical system. So anyway, let me move on. We can come back to this in discussion. So this is the initial parameter space for the angular velocity and the upwards velocity. And every one of these regions corresponds to heads up, tails up, heads up, tails up, heads up, tails up. And so you see what happens if the initial distribution over upwards velocity and angular momentum is a smooth distribution over this space. What you get in the end is you just sum up the areas for heads up and tails up, and you get 50-50. You get an exact weighted average of 50-50. But this is all predicated on the idealizing assumptions we made at the beginning. And if we hadn't made those idealizing assumptions at the beginning, you may not have gotten this at the end. And I can already tell you that if you don't assume that the center of gravity is the geometrical center, you're not going to get this. And that's the case of a bias coin. You bias a coin not by loading it on one side, as people think, but by twisting it. That's how you bias a coin. Okay, so it's a lot more complex, the tossing of a coin, that you may have thought, and actually getting the 50-50 probabilities out for an unbiased coin is a hard exercise in complex dynamics. It's not as simple as you may have thought. And in this hard exercise, you're distinguishing implicitly the propensities, which are all those assumptions that you're making when you idealize the coin at the beginning. They're ascribing propensities to this coin as described in this model. You're distinguishing those assumptions that you make about the coin from the probability 50-50, which is actually the outcome of the complex dynamical system. And it could have been very different if the propensities had been different. Those probabilities for heads up and tails up would have been different. And then that, in turn, has to be distinguished from the frequencies that you get when you run the experiment repeatedly on the coin and you toss it repeatedly, say 1,000 times, and you get 505 heads and 495 tails. That frequency statistic is distinct from both the probability and the propensities that describe the nature of the object that's being tossed. So you really need to keep these three different in order to make sense of this coin toss as a complex dynamical system. That's really my main claim. I think I could finish my talk here, but let me continue and say how is it that I like to interpret this. I like to interpret this as making the implicit claim that the propensities somehow ground or generate, and here we can discuss the exact philosophical nature of this relationship. Rivers of ink will be spilled on this before we come to an agreement. But there's clearly a way in which the propensities are absolutely indispensable in order to get the probabilities out. And you can see that in the way that we model the phenomenon. You need to make the assumptions to begin with. If you don't make any assumptions or suspend them, you get no probabilities out. So there's a sense in which these assumptions about the propensities or properties of the coin are acting as generators of the probabilities for the coin landing heads or tails. And then together, these single case chances with the underlying propensities of the coin, they seem to say something that's predictable and can be tested about the frequencies that should be generated in an experimental run on this coin. And I would have to think that that relationship must be explanatory. If you toss a coin and you get 890 heads and only 110 tails, you want to explain that somehow. Maybe you can run through your model again and see whether the propensities of this coin are different to the ones that have been described in the model, and whether you can construct a different model that would generate these different statistics and therefore explain the difference in the statistics. I guess that's what you would like to do. And what that suggests to me is that the propensities and the single case chances together must explain the frequencies that come out of the experimental trial. Okay, and if you follow me here and I've convinced you about the coin toss, then all of scientific and statistical modeling is like this. A little bit more complex, yes. The systems are a lot more complex, yes, but not actually so much more complex. And in all cases, you're going to have to make these distinctions if you want to make sense of what goes on in quantum physics, evolutionary biology, and all kinds of different areas where we use statistical modeling. In the case of the coin's propensity to land heads for a particular toss, one very important observation that follows from this is that the propensities need not explain why a particular coin lands heads or tails on a particular toss. And this is a requirement that has been imposed on propensity accounts of probability, which I think is rather unfair. I mean, there's no reason why the propensities of the coin have to explain to you why, in this particular case, it landed heads or tails. What it has to explain is the long-run frequency statistics for running an experiment on the coin. So this is not really very different from quantum mechanics, right? I mean, we know in quantum mechanics that the atomic description of the structure of an atom or an element cannot prescribe and predict whether it will radiate in the next hour or no. It can only predict the probability for it radiating in the next hour. And that's, I think, as it should be. Propensities are in the business of explaining frequency statistics, but not actual particular individual outcomes. It's true for the coin toss. It's true for the radioactive atom as well. It's a model as a whole that will explain the long-run frequency statistics. So this is my latest account, the one that comes out in the paper that I just published. The propensities generate the sample space because they delimit and quantify the realm of possibilities for a chancy phenomenon like this. And I like to think now of propensities not as particular idiosyncratic properties of objects, but as abstract designators for whatever properties the coin has that generate these probabilities or single case chances for a given toss of the coin. What are these properties? I don't know. They may be very different for very different systems. The only thing they have in common is that these are the properties of the chances systems that generate the probabilities. And in different cases, in quantum physics, in evolutionary biology, in the case of the coin, those properties may be very different, mechanically very different. Electromagnetic properties may be very different from mechanical properties. They don't have to be always the same sort of property. Propensities are just a collection of properties of an object that generate reliable, probabilistic, single case chances over particular outcomes of experiments we do on those objects. And they may be very different properties in different cases that are instantiating these abstract propensity designators. So nowadays, I like to think of propensities as abstract labels for whatever properties are going on at the concrete level of a particular system that generate these single case chances. And what they have in common, these properties, is only their function to generate these single case chances over certain events. So I have no problem saying that the radioactive atom has propensities, and the half-lives of radioactive atoms are the result of certain propensities that the atoms have. And those clearly are very different to the case of the coin, where the underlying propensities obey certain deterministic dynamics, but also serve to generate reliable, steady probabilities over certain outcomes. I call them all propensities because they're defined by their function to generate these probabilities over these outcomes of experiments or events that happen when we put them in certain experimental setups. Very different underlying mechanisms may give rise to propensities in all cases, in very different fields. Okay, so the question whether this is an objective or an epistemic possibility that underlies propensities, and I want to keep an open mind about this and be as neutral as possible and as accommodating as possible. I don't think it really matters much whether they're objective or epistemic possibilities. The thing that turns them into propensities is the fact that at the abstract level, they're the generators of these probabilities. So there's a big discussion about the nature of the objective possibilities that presumably inform objective probability. And I want to completely bypass this huge debate by just keeping the account as neutral as possible. There is this question about nested models that I referred to before. What do you do when you have nested models where you have models that epistemically describe probabilities of certain objective probabilities obtaining? It's very common in science. You have models where you describe certain uncertainties about objective parameters. And my suggestion is you just use a multiplication rule. I don't see why that shouldn't work there. If you want to compute the final probabilities, just multiply the epistemic uncertainties times the objective chances that you're dealing with, and you get a final description of the overall probabilities. We obviously will be hybrid, partly epistemic, partly objective. But I really don't see a big problem with this. So people who work on the models for climate change, for instance, where they have to do model ensembles and quantify uncertainties, or objective probabilities have to do this, and I don't see why this could impugn any account of propensities like the one that I've given here. You just multiply the probabilities. And finally, just to say, in practice, of course, this is extremely complicated. When you're producing models for these propensities, how to get the probabilities out of the underlying propensities of the systems is really hard. And you've seen it in the coin toss. Even for a coin toss, you have to make all this bunch of idealizing assumptions, run a dynamical simulation on the system, and with some luck, you're going to be able to prove something like this theorem that comes out of the method of arbitrary functions that will give you reliable objective probabilities.
Can you just define what's real system from your perspective? I mean, you mentioned real systems. What's real systems from your perspective? What do you define as real system?
Yeah, the coin in flight.
Oh.
That's a real system. And you want to describe it probabilistically, then you're going to have to apply specific probabilistic models to this abstract theory or description of the coin toss. And so this is not easy in practice. It's a really hard thing to achieve. But this is precisely the art of statistical modeling. It involves putting all these pieces together in a way that gives you reliable results at the end. And so I'm not suggesting that the statistical modeling is easy or easier once you have these distinctions in place. It's really hard, but at least as philosophers, we can make some headway thinking about this in terms of these distinctions. So I like to think that Paul sort of endorsed some of the picture that I'm providing here. He certainly was very happy with the distinction between propensities and probabilities. He had his own way of understanding that, not necessarily mine, but he went along with that, and we had long conversations about that. And I like to think that this is also something that I can defend. So I'll finish this. I think I'll finish here because I can tell you how this applies to both quantum mechanics in more detail.
Evolution is enough.
Evolution is enough.
Is it? Don't do quantum mechanics.
This is enough. You want me to do this?
Want to take them both?
You think about it. So anyway, what I've done in some of the detail, the stuff that I've done around here is to try to apply this schema to both quantum mechanics and half-lives for radioactive elements, and also in the context of evolutionary biology by thinking of fitness, evolutionary fitness, as involving this tripartite distinction. And I'll just summarize everything that goes in that slide by saying this. Philosophers of biology have had a long debate, by now very, very long, on the nature of fitness. And there's awful disagreements there. I mean, I thought philosophers of physics were really bad, until I started interacting with the philosophers of biology and realized, bloody hell, those guys really fight. And so there's this huge fight in the field about whether fitness is the underlying properties of the organisms that are fitter or less fit, the probabilities for successful reproduction of the organisms, or the frequency statistics, the actual measure of successful reproductive outcome of those individual organisms. And there's these three different schools. One of them thinks of fitness as a property of individual organisms. One of them thinks of fitness as successful reproductive outcome or output that you can measure in any given biological environment or context. And others think of fitness as the probability or the expectation for that reproductive output, but definitely not the reproductive output itself. And they have these terrible quarrels between the three schools. And one of the nice things about my account is that I can go to them and tell them, but you're all right. You all are right. I mean, fitness is a propensity. Fitness is a single case chance. And fitness is a frequency statistic. in fact, it's all three things at the same time. And if you don't think of the three of them together, you're not going to make any headway. Fitness is a way to attempt to describe the relationship between these three different notions. And if you just follow the discussion in the philosophy of probability, you have noticed this a long time ago, that you need to distinguish the three different notions. And you're all correct. You don't have to fight. You can all be happy together. So that's my happy concluding notes. I mean, now I apply this project wherever I go, trying to make quarterly parties come together. And I'm a peacemaker now. I'm a peacemaker. So that's the conclusions. But the conclusions just wrap up what I've been saying here. I'll just finish here. Let you ask me this.
Yes, thanks. I think I expect you want to help.
There was. I'm not wanting. I don't want to say.
5 years.
Yeah. Sorry.
Go ahead.
No.
I think I agree with your comment. It sounds very reasonable to me. But I wonder whether it is really necessary to involve the details of mathematics in the case of the coin toss, because it seems to me that the everyday physics, so to speak, folk physics, the physics that we can gather simply by interacting things around us, is enough in order for us to feel that the certain propensities in the coin determine the distribution of possible results. And so I wonder whether you're using the mathematical model in order to bring home this realization that really the propensities in the coin determine the distribution, or whether you think it's really part of your account that there is this more mathematical and explicit apparatus that gives you those things.
Yeah, I do think that you need that complex dynamical system to make sense of the ascription of probability one half to heads and tails. And I think the intuition that you're talking about, it's either a prejudice or schooled by past experience and induction on coins. And that's not the same as having a full account of how the propensities generate the probabilities. That's just your inductive experience of frequency statistics in the past. And I'm prepared to accept that that creates an expectation, of course, an inductive expectation that similar coins will behave similarly in the future. But I don't think that gives you any full understanding of what the phenomenon is like. For that, you need the complex dynamical system.
But everyday experience is not just tossing the coin many times. It's picking it up, seeing that it's happening, seeing similar objects flying into the air.
Yeah.
There's a lot of observation that feeds into this everyday physics.
Yeah, I mean, there's a lot of observation, but none of that is explanatory. I mean, that's just induction when it's kind of general work in generating expectations. And I agree. I mean, I am a believer in induction, but I mean, like you, I think we don't know why we use it, but we use it, and life would be unbearable without induction, because we wouldn't be able to rely on our expectations. I believe all this is true, and of course we've tossed coins many times before, and children are told, and maybe they do toss coins. I don't know how many coins we actually toss, we have the sense that we have a lot of inductive experience of coin tossing, and that creates expectations. I agree with that, but none of this is explanatory. No? I mean, this is just inductive expectation. If you want to explain the phenomenon, I think that's where you really need a dynamical model, and we've been lazy about this because we've got this trivial system. It's amazing to me that it took all the way to 1986 to have a full dynamical model of the coin toss.
I think most people do have dynamical models. It's just that they are not as explicit as well developed as around the tube shot. I think that a jellyfish with the induction of a jellyfish, we have to use mathematics in order to get what we get, simply because we are a certain entities and we have certain typical experiences in the world. So I'm not saying that mathematics does not add. I'm just saying that in certain circumstances, the arguments would use less, would work with less, let's say.
Well, I don't know whether to take this as a kind of nice compliment invitation to maybe it's even simpler. Maybe so you're saying I can convince, I will have being able to convince you all with less. All right, maybe that's good. So the conclusion is true, but I didn't need this long elaborate argument to get there.
No, it was helpful. I'm not saying anything critical. Maybe I think you're.
Yeah, maybe. Well,
Maybe I can help you. Because I'm not sure that that we need to disagree with each other. Because it seems to me that if you will check all the assumptions of the and where they are coming from, the mathematical model, you ask yourself, I mean, why is it? For example, when we talk about the contours, just to give a simple example, not going into all the details. Basically, the two states of the end states, tails and heads, are macro states in the phase space, two regions.
Yeah.
That the coin, the trajectory of the coin with the light after the crossing. So you divide the space into these two. And essentially what you're doing, and then you're giving the detail, you can give a detailed mathematical model, is that you construct the model in such a way that the two macro states are of equal size. And this will give you basically essentially it will give you the equal chances.
Yeah.
Because they are of equal size and there are no other options for the trajectory to go to. So and that's it. But I think that if you think why are they of equal size? Why do we need to choose a measure? To measure the size of these two infinite sets, because they are infinite.
Yeah.
And the question is, why do we choose a measure which gives equal size to these two sets? Because we could have chosen a measure according to which they don't have the same size. That's the mathematical part. Well, the reason is because this is how it figures in our experience. In our experience, when we actually, play with points, we see that it's a 50-50.
So maybe,
So actually, I think that it is right that when we, especially for these cases where we take some sort of classical models, we would give a nice, elaborate mathematical models which formulate in much detail. That's very nice and trivial to do, but still they formulate our experience.
yeah. So
They don't explain.
thank you, Mayor. So maybe now I think I understand your question at the back of the room.
Yes.
Your question better. So the question is, this model doesn't make any new predictions. This model is just accommodating what we already know is the case, that if we toss a fair coin, the probability of heads and tails is 50-50. Yes, indeed. I mean, this is an exercise in generating a new model that will have incredible new predictions that we haven't known before. This is one of those cases where you build a model in order to explain phenomenon that you already have a lot of evidence for, and you have a lot of confidence in, on that, I guess, on inductive grounds or other sort of theoretical grounds.
But it seems like you're going to undermine your account, because when you look at the coin and use experience, you just use principle of indifference. It's very primitive. You don't use any dynamic model.
Well,
No, but then you can ask about the question. It's not good.
I am, and I'm not so sure,
Because it's about you.
but I'm not so sure that we do. I mean, it's an interesting question what children do when they predict the outcomes of things, of simple systems like this. And it's not clear to me that they just apply a principle of indifference. Michael Strevens is very good on this. He's written a couple of thick books on this. And he claims, and this goes back to that question as well that I was asked in the talk. He claims is our experience with dynamical systems, it's our experience in throwing things and seeing how they behave that really informs our expectations in the coin toss. It's not any principle of indifference. He claims it's not about observing the symmetries of coins and then running a principle of indifference on the symmetries of the coins. It's about actually doing things with objects, gaining inductive expectations out of doing those things with those objects. So he claims it's all wrapped up with our complex dynamical interaction with these objects. And he thinks this is true for coin toss and also for dice. Throw a dice, you have this little cube where you put the die and throw it. And that also has to do with the experience of how uncontrollable it is. When you shake your hand, you have no idea what the initial condition. You can't control the initial conditions of the object. That comes out. And what that indicates for Strevens is that the initial probability distribution that goes over that space distribution of values is objective, where Strevens does not epistemic. So although it's a deterministic system, the chances that come out at the end are fully objective and ontological because they're the result of an initial objective probability distribution over our actions. And so he claims it's objective fully. The story is fully objective because there are objectively uncontrollable actions that determine dynamically those probabilities. And our expectations are informed by those actions. He goes into a long discussion of the psychology.
We have a lot of questions.
So I mean,
I saw modern art in the book, and I wanted to ask if you are pluralist in art and philosophical sense.
that's changing the topic completely because this is inference and representation.
So it's pluralism.
Yeah, I'm a pluralist about. The story is a little bit more. I mean, this is about modeling and representation. It's a different topic, but the short answer is I am a pluralist about representational means, something I call means, but I'm not a pluralist about representational constituents. I'm a deflationist about representational constituents, and I really have to give you a different lecture here to explain these concepts because they belong in a different domain. I'm connected with this idea of probability.
So many questions come to mind. It's not as simple as it seems, right? But so I'll ask something very specific. How do you think in this scheme do you think about conditional probabilities? Are they only at the formal level or at the propensity level? Where can we shop?
Yeah, great question. Great question because a lot of people have tried to formalize propensities as some sort of conditional relationship that generates conditional probabilities. So conditional probabilities on this account, they have no intrinsic relationship with propensities. Conditional probability is a formal description of probability statistics on a given pre-antecedent condition. And there's no reason why the pre-antecedent condition has to cause or be partly a cause of the condition upon event. So if I write a probability of, if I write here, can I write here? Can I write with this?
Yeah, try.
Yeah, so if I write probability of A given B, there is no reason on my account, whatever, why this has to be a cause of this. And there's no reason on this account, whatever, why this must be a propensity for this to happen. This could in fact happen after this, and it could be well defined. It could be a conditional probability where you're conditioning upon the causes upon their effects, and you can get a perfectly legitimate probabilistic description of that. And I don't have any quarrel with that. And I don't have to have any quarrel with that because I don't interpret this probability function as a propensity. People who do interpret this probability function as a propensity have a problem. Because if you think this function is a propensity, then you must think that this is the underlying propensity that causes this. But you can never accept the other way around. And so one of the reasons why you cannot identify probabilities and propensities is connected with this interpretation of conditional probabilities. And Wesley Salmon showed us that there are many cases in which you can have very well-defined conditional probabilities where the condition upon event is in no way a cause or a propensity for the event of this condition. So what is the probability? I mean, Salmon's examples is a Midwestern American, and some of his examples involve shooting things, and so what's the probability that I shoot somebody and kill them? You say, well, that's the cause, that's the effect. But then you could also define the probability of having shot someone who dies, and that's not ordered in the right way in accordance to a propensity interpretation. So this is one of the reasons why I don't think probabilities and propensities are the same thing. There are further reasons.
But conditional probabilities and probabilities are the same thing.
Yeah, conditional probabilities are probabilities.
Yeah, so they all live at the middle level of your 3-pi type.
Yeah. Exactly.
Thank you. I'm convinced, but I want to say that I think you must take side on the objective, subjective, objective epistemic debate, because you are epistemic. You can't claim that you are counted of objective probability, because like what we call propensity are not dispositional properties of the object itself. These are not properties of the coin. The coin is not the system you described there. What you described there is an idealized model, which, given all of our lack of knowledge, as Schwarz said, that we sort of like put in the model as idealization. These are where what you call propensities come from. Because it's just the lack of full knowledge of the initial conditions that we sort of like gloss over and make all kind of simplifying assumptions about, and then suddenly we get a space of possibilities. But that's all epistemic. These are what you call propensities are properties of the model, not properties of the thing, of the target system. Therefore, I'm not so sure you can call it objective in like.
I mean, I think I see what you mean. I would think that they are properties of the object according to the model. I mean, my model describes the object as endowed with these properties. And then the question is there any way to describe the properties of anything other than by means of some representational model? Suggestion is that perhaps not, in which case you cannot get away from describing the properties of things via some description, representational model of that thing, in which case I don't see the difference anymore between saying that this is the collection of properties that the thing has in itself, and this is the collection of properties that the thing has as described in my model. Every description of the properties of anything is via some representation.
Yeah, but descriptions are like a thing. They are not a thing. The distinction.
Oh,
the propensity.
okay, but but this is hold on. I mean, yeah. I'm not saying that we can have full and definitive or conclusive knowledge of anything. So it may be that our epistemic condition is always one of ignorance. The question is, what is it that we're ignorant about? And I would think that there's a difference between being ignorant about the objective properties that something has and being ignorant about what kind of knowledge somebody has about something. So I'm not saying that we can get to know all the properties of any coin with absolute and infinite precision. But there is a difference between saying, I don't know exactly what the propensities of that coin are, and saying, I don't know what kind of knowledge people have about that coin. So, and I'm just claiming that when you profess to have ignorance about the propensities of the coin, you're professing to have ignorance about objective properties of that coin. And propensities are objective there. And if what you get at the end is a probability, then you have to ask yourself the question whether the probability is the outcome of the properties that you're ascribing to the object under some representation and therefore giving some ranges of uncertainty, or whether it's a property of just your lack of knowledge. And I think those are different claims.
Can you give an example or something that is different?
Yeah, I mean, suppose that you toss a coin, but you don't tell me what coin it is, and you don't tell me with what strength, and you don't tell me where it landed, and you ask me, did it land heads or tails, and what probability did it have for heads or tails? And given all the uncertainty that I have, which is clearly epistemic because you're not giving me the blank information, then I say, well, I don't know. I'll just say probability 50-50 because there's so much that I just don't know in the description you're giving me. That's epistemic. But then
it's just a different degree. You have less information to put in your model.
No, but this has already happened. There is one.
Still, but you're talking the description of something, right? It's just saying, I don't know how thick it is and where you put it. So it's just the model has less information.
Not a description, everything is a description.
No, so this is a table. This is not a description of the table.
yeah, good. That's exactly what I was saying. Thank you.
So I have a related question. I think it's related. So when you use the language of propensity, you create an analogy between, it's not an analogy, it's a dispositional property.
Yeah.
And metaphysically, you think about dispositional properties in a different way from, say, categorical properties or
Yeah.
other properties.
Yeah.
There's something about the object which you can describe only by saying what it does. Or only by saying what it does under certain conditions. But your account seems to suggest that when I ascribe a propensity to a system, it's in virtue of its representation that I ascribe the propensity to the system. And then it makes less sense to think about it as a dispositional property, because it's not something that the system has, and because it has it, you know that under certain conditions it's going to behave a certain way. It's something that you are ascribing to the system in virtue of the fact that you have a model and you have a representation, and the representation cannot track everything. I don't think it leads you to necessarily saying that probability is subjective, but it does suggest that your language of dispositional properties and your language, the propensity generates, that's the language that you use, it's a causal language. It seems not the right language to use if the propensity is something that you ascribe to the system in virtue of the model.
Yes. But yes. But why is it that you think, I would counter, why is it that you think that all the properties that the model ascribes to a system must be categorical? Because I think it's the presumption in your question.
Because that's how you describe the model. That's what the model is. The model itself is not.
So the only
It's not. You're explaining the propensity. You are ascribing the propensity in virtue of the model, but the model itself is not a bunch of dispositional properties.
I mean, do you think that we cannot have models of, say, fragility?
Usually the model
I
is
represent the fragility of a glass in some model, representation of the glass? Because the only difference that I see between dispositional and categorical properties is that categorical properties are instantiated fully at every instant of the life of the object that possesses them. So the table is a square, and for as long as it's square, it's instantiating that property, and in fact, it becomes an observable property. The glass is fragile, but it is fragile only because under certain circumstances, it would instantiate breakage. And the only difference that I can see between a dispositional property that's described and a propensity is that the propensity only instantiates breakage with a certain probability. If fragility was a propensity instead of a disposition, glasses would break with a certain probability when we hit them really hard with a hammer that fulfills all the conditions, the antecedent conditions for the disposition to be manifested. So, you know, in the description of dispositions, we have testing conditions. If the testing conditions obtained, then the disposition is manifested in the manifestation property. So fragility gets manifested in breakage when I hit the glass with a hammer sufficiently hard, the testing conditions obtained. In a propensity, the manifestation is only with a given probability. So a quantum glass, which had propensity to fragility and not a disposition of fragility, could break when I hit it really hard with a hammer only a percentage of the cases. A quantum glass is one that surprises you because you hit it really hard with a hammer and said, "There's no way that this is not going to break. It's fragile." But occasionally it stays. It doesn't break. It's only 90% of the time that it breaks, and that's sufficient for the quantum glass to have the property of fragility, and that's a propensity. So if we can model dispositions, I think we can equally claim that we model propensities. I don't see the difference. The only difference is when you're modeling propensities, you have to use probabilities.
But then there's no difference between the propensity and the probability.
No, there is a difference. There is a difference because this is on my count, this is the propensity, and it generates the manifestations with a certain probability. But this does not need to have a probability, and it's not a probability, and need not be in the sample space of any probability function. It's what generates the probabilities and the sample spaces. So if this is a quantum glass, this is the atomic structure, this is fragility, and it breaks with a certain probability. But they're not identified, they're not the same property. This is a different property, this is a different property. And the property of having a certain probability is a different property. They're not the same. On this account. Yeah. So,
Yeah, thank you. I would like to return to two things which are quite basic, or one thing which is discussed, and one thing is quite basic, the role of the frequency statistics or statistics here.
Mm-hmm.
And I return to this model that you put, all the discussion that he had there, and then I'll see why it does. Because what I think is that here I'm a little bit with around this. You don't need to have a specific model in mind. I think that once I know physics, even without seeing any tossing of the top of the coin, I can see from the problem that I have a symmetric coin that is giving some kind of initial velocity around its axis, that the chances that it falls at one side or the other are equal, if it is symmetric. I can think if there is enough time that there are many, it's enough, once there is enough time that it goes, and since I don't know exactly the initial conditions, it's equal chances. I don't need, so for that I can have the probability. I can know how I can think of any probability of any case. But then I don't understand where the frequency goes. Is it something part of it, or is it only the way I measure? Because also if I toss 100 times, I won't get 50. So there's a chance I get 50, but there is equal chance I get 40, or a little bit lower, I got 49, or higher chance I get more or less than 50.
Yeah.
So where the frequency goes?
Well, this is going to depend on whether you think of the frequencies as finite frequencies in finite sequences of the experimental run. And so, I mean, those of you who know a little bit of the discussion of probability, there are people who call themselves finite frequentists. And then the finite frequentists, there are people who call themselves finite frequentists. They say, I'm a finite frequentist. And then there are people who call themselves hypothetical frequentists and go around proudly. And then there are the limiting frequentists, right? And they disagree. And some of them think probability is just any finite frequency that's sufficiently large. And you can identify.
How can that be consistent?
Yeah, I think the theory is crazy and there's lots of arguments against it. But if you're a very strong empiricist and you think that only quantities that can be measured can inform our scientific concepts, and you're going to want to reduce probability to these finite frequencies. And you're going to say, well, if I toss the coin sufficiently many times, and the question is how many is sufficient. But say 10,000, then what I get is a probability. So 501, 499, 1,000, that's the measure, that's the probability. There's nothing else to probability on this. But then there are people who claim that's not enough. You have to take this to the hypothetical limit in which you toss the coin an infinite number of times. Of course, nobody has enough time in their life to do that. But but the probability only coincides with the hypothetical frequency, right? And these are the hypothetical frequentists. And these are different problems because for start, it's not empiricist. You need to appeal to modalities before you get started.
It's like a propensity.
Yeah, and in the end, it's even worse than the propensity. The modalities are even harder to explain. So why do you go through all this trouble when you can just appeal to propensities? That's what I was. And so, it's really, I mean, frequencies look very simple. You say it's just a matter of counting, but actually they're not that simple. And when you want a full theory of probability in terms of frequencies, it gets hideously complicated. On my account, I can keep things simple. Because because I'm not a frequentist about probability, I don't think probabilities are frequencies, either finite frequencies or hypothetical frequencies or limiting frequencies. I don't think probability is any of those things. I think probability is a theoretical construct that appears in our best statistical models and is well defined by the Kolmogorov axioms. And it's implicitly defined by those axioms, and I have no need to say anything else. I don't need to interpret probability. I am one of those people who claims probability is not something that can be given a philosophical interpretation. I'm not the only one. There are other people like Elliot Sober. So frequencies is just what you measure in the lab. I think they're finite. We measure them all the time in laboratory experiments. And they're incomplete information because we cannot run these experiments forever. So we're always going to have to stop the experiment at some point. And what you're going to get is always a finite frequency.
So if I do an experiment,
yeah,
quantum mechanical experiment, or I don't do, I give you a scenario.
Yeah.
And I know what's the probability.
Yeah.
So there is no place for the frequency also in your place because there is not. We didn't do it, so that we didn't measure. We will agree what is the probability because we have the model.
Yeah.
So there is a propensity.
There's a propensity, there's a probability,
but no frequency.
But you have no frequency. And then what you cannot claim is to have experimentally validated your model.
Yeah.
And but you have all the full concepts. You have the propensity, you have the probability.
You don't have.
Yeah. And you don't have frequencies because you haven't run a single experiment on that. That's not a problem on my account. If you want to test your model, then you're going to have to run an experiment and then you have frequencies. And then you're going to have to apply something like the law of large numbers to claim that your experiment is sufficiently large that you're approximating the underlying probabilities and it's sufficient evidence for the model, but there are always going to be judgments as to where you run the experiment, and you're never going to be able to run the experiment forever. So yeah, that's in the nature of frequencies. So on this account, frequencies are always finite, but that's all right because we're not identifying probabilities with them. We're not trying to give an account of what probabilities are. You know, so they're just experiments.
We're out of time, unfortunately. We have a few more questions, but we ran out of time. So
Oh,
thanks very much.
I was enjoying myself. Thanks so much.
Question?